So we'll continue with our lecture and find the time complexity of the FFT algorithm and take some examples. So first we observe that we have divided the problem for finding DFT of fx. So this is the original problem. This is converted into, so the divide step involves computing DFT of two smaller problems, even and odd parts. DFT of FE of x and DFT of FO of x. The original problem has vector of size length n. For smaller subproblem, problem size is half n by 2. So in divide step, we divide our original problem of computing DFT of fx into two smaller subproblems of half the size, DFT of even coefficients and DFT of odd coefficients, each of size n by 2. So this is the divide step. Then the recursive step is compute these DFTs, the smaller DFTs. So we have recursive step. We compute the two smaller DFTs. First is DFT of FE of x and the second is DFT of FO of x. So we recursively solve using the same FFT algorithm. We recursively find DFT of FEX and DFT of FOX using the same FFT algorithm. And finally we combine the results. So the conquer step, how we combine the steps. So for conquer step, we already know the smaller DFTs, the two DFTs, DFT of FEX and DFT of FOX. We know the values and we need to combine them. So just remember what are the DFTs of FEX and FOX. So as a vector, they are point value form evaluated at n by 2, n by 2th root of unity. So just remember what is DFT of FEX and DFT of FOX. So we write the values computed DFT of FEX as a vector. So this will be FE evaluated at omega n by 2, which is n by 2th root of unity, and all powers starting from 0 up to n by 2 minus 1. So this vector we get as answer. Then FE of omega n by 2 to the power 1, continue up to FE of omega n by 2 to the power n by 2 minus 1. So this is the vector we get for FE. Similarly, DFT of FOX, write their values. We get very similar values. FO evaluated at omega n by 2 to the power 0, FO evaluated at omega n by 2 to the power 1, continue up to FO evaluated at omega n by 2 to the power n by 2 minus 1. So we have computed DFT FEX and DFT FOX recursively using the same FFT algorithm. We know the values. Now in conquer step, we have to combine. So how we combine? So again just remember that what is value of DFT of fx. So DFT of fx is a vector of length n, which is defined as f evaluated at omega n to the power 0, f evaluated at omega n to the power 1, continue up to f evaluated at omega n to the power n minus 1. So the original DFT is of length n. The smaller DFTs are of length n by 2. And how we combine them? So we use our earlier properties, the relation between omega n by 2 and omega n. So using these, the conquer step, how we combine the calculations. So these values from 0 up to n by 2 we divide in two parts, first half and second half. So for 0 to I up to n by 2 minus 1. So first half we compute using the formula f of omega n to the power I is equal to fe omega n by 2 to the power I plus omega n to the power I times fo omega n by 2 to the power I. So these are first half set of values, and for remaining, so for first half set of values, as I varies from 0 up to n by 2 minus 1, so these values, fe and fo values, we are having n by 2 values from the smaller DFT of fe and fo. So this is for first half. For second half, just use our earlier observation that omega n, so we can write this here itself. The second half set of values, omega n to the power I plus n by 2. We get again the smaller FFTs are repeated, fe of omega n by 2 to the power I minus. So why minus? Just see, it is actually omega n to the power I plus n by 2. This is second half value, fo omega n by 2 to the power I. So there is no need to calculate this. We can simplify, as we have seen earlier that omega n to the power n by 2 is minus 1. So just flip the sign. So it flips the sign and we get fe of omega n by 2 to the power I minus omega n to the power I fo omega n by 2 to the power I. So this way we get the complete DFT. So first half set of DFT, first half of the DFT, original DFT, we get by adding the corresponding values from fe and fo, the corresponding values, as I varies from 0 to n by 2 minus 1. Find fe value, corresponding fe value, find corresponding fo value, use this formula, multiply fo value by omega n to the power I and add. For the second half set of values, again very similar, just flip the sign. Find fe values, find fo values, these are repeated, and just flip the sign, multiply by omega n to the power I and flip the sign. So this way we get complete set of value. This is conquer step. Now we find the time complexity of FFT. It is very easy. We have two subproblems, and conquer step we can easily see this is repeated twice. So we are performing some theta of n computations in conquer step. In divide step also we can easily see. Divide step is basically dividing into two subproblems. This again takes linear in n time. So now we can write the recurrence relation and solve it. So for basis is very simple. When n is 1, there is no need to subdivide the problem. We have just observe what is DFT of a constant. So this a is actually a constant, fx equal to a. So when you convert this into point value form, take any point, you always get a. So our observation is for base case, DFT of a single value is the value itself. So this is our observation, and now we can write the time complexity. So for basis case, we can take complexity as a constant d, otherwise we can take, so now we get this recurrence relation. Tn is equal to 2t, we have two subproblems of size n by 2 plus Cn. Cn is the total time taken in divide as well as conquer step. This is when n is greater than 1. Otherwise it is a constant when n is equal to 1. Now we solve this by recurrence tree method. So we start with Tn. This becomes, at root we have Cn, it has two children, Tn by 2. Again we continue like this. Root we have Cn, next level Cn by 2, and so on, continue like this. Next level Cn divided by 2 square, and so on. Continue, find the total cost at each level. We have a simple observation, total cost at each level is constant, the same Cn. So first level we have one problem, one node of cost Cn, we get Cn. Second level, this call it level 0. So for level 1 we have two subproblems of cost Cn by 2, total we get Cn. Continue like this. Level 2 we have two square subproblems of cos Cn by 2 square, total again we get Cn. Continue like this at the general level I. So level I also we can write 2 to the power I subproblems of each having cos Cn divided by 2 to the power I, total we get Cn. Continue like this. So this continues up to just before the leaf nodes. At leaf nodes it changes. So for leaf node at level log of n with base 2, we get cost is d, number of subproblems is 2 to the power log of n with base 2. So we get dn. Now we add everything and get the time complexity. So we write the expression as Tn is equal to sum of I is 0 to log of n with base 2 minus 1 Cn. plus dn. We are getting a geometric series. No, not geometric series. Same term repeated log n number of times. So we get Cn log n with base 2 plus dn. So we can remove the constants and write this as simplified format, big theta of n log n with base 2. So the FFT complexity of the FFT algorithm is n log n. So using FFT you can compute the DFT of a vector a0 up to an minus 1. Again, using the same algorithm we can also compute DFT inverse a0 y0 up to yn minus 1. So idea is exactly same. Use the same recursive algorithm. So here the only difference is when using FFT algorithm for computing DFT inverse. So what we have to do is just flip the powers of omega. So the only difference we have to make is just flip the powers of omega. Means instead of using omega n to the power I, we should use omega n to the power minus I. This is first change that we have to do. Second change, only at the final step. Only at the final step, not intermediate step. Divide the result by n. Divide the result by n. So these two changes if we do, just use reciprocal powers and at the last step divide by n. We get our inverse DFT using the same FFT algorithm. Now we'll see some examples of computation using FFT. So the example we take the same two polynomials, f1x as x plus 2 and f2x as 2x plus 3, and multiply using the FFT algorithm. So first we take f1x is equal to x plus 2, and we take f2x as 2x plus 3. So now the problem is compute their product f1x multiplied by f2x using the FFT algorithm. So first we need to convert them into coefficient form. So x plus 2 we write in coefficient form as 2, 1, 0, 0. So x plus 2 is actually only, we have seen earlier, it is only the vector 2, 1, but since their product will have 3 terms and we have to pad it up to the nearest power of 2. Nearest power of 2 is 4. So we have to use vectors of length 4, so that we can apply the FFT algorithm. So x plus 2 we write as the vector 2, 1, 0, 0. Next we have 2x plus 3. 2x plus 3 we write as the vector 3, 2, 0, 0. Now the idea is how you multiply So this FFT algorithm will perform multiplication in only big theta of n log n basic operations. So the idea is first compute the DFT. So these are the steps. Step 1, compute DFT of first vector 2 1 0 0. Suppose we are getting these values y0, y1, y2, y3. Second step is compute DFT of the second vector 3 2 0 0. DFT of 3 2 0 0. Call it Z0, Z1, Z2, Z3. So both steps 1 and 2 take big theta of log n time. So these steps will take big theta of n log n for computing the FFTs. Step 3 is we multiply the polynomials we multiply the DFT of the two polynomials. Step 3 is compute their product in point value form, DFT of 2 1 0 0, 2 1 0 0 multiplied by DFT of 3 2 0 0. So this is pointwise multiplication. So it will be y0 z0, y1 z1, y2 z2 and y3 z3. So step 3, it requires only big theta of n time. Now the final so we know the product in point value form. So to recover the polynomial in coefficient form, we have to find DFT inverse. So next we find step 4 is find DFT inverse using the same FFT algorithm of this vector y0 z0, y1 z1, y2 z2, y3 z3. So we get this in point value form. Call it a0, a1, a2, a3. So point value form, we recover our product a0 plus a1x plus a2x square plus a3x cube. So actually we will get only polynomial of second degree, so that a3 will be 0. So step 4, again DFT inverse takes the same time complexity, big theta of n log n. So in this way, all these 4 steps combined, steps 1 to 4, total time complexity is big theta of n log n, basic operations of addition and multiplication. So this is our idea, and we start with our first DFT, computing DFT of 2 1 0 0 using the FFT algorithm. Using FFT. So our original problem is 2 1 0 0. This is our original problem. So we divide this into two smaller subproblems. We separate even and odd terms. The even coefficients are 2 and 0, odd are 1 and 0. So we separate them out and write this as 2 0. This is first level of divide step, and 1 0. Again we do the same thing. Separate them into base problems. 2 even portion, odd portion is 0. Here also 1 and 0. 1 and 0. So divide step is very simple. At each step simply separate odd and even coefficients. Now for conquer step, how we combine. So for combining, so just remember, for base case, FFT, DFT of the vector, a single value is the value itself. So DFT of 2 will be 2, 0 will be 0, 1 will be 1, 0 will be 0. This is base case. There is no need to further subdivide it. Now in the conquer step, how we combine. So first level of combination, we should get a vector of length 2. Means we have value of n is equal to 2. So for n equal to 2, we compute omega 2. This we have already computed. We know that omega 2 is e to the power 2 pi I by 2. We get e to the power I pi. We get this as -1. So once again, just see our original equation, how to combine. We have this. So first half we use this. The corresponding DFT values are combined with omega n to the power I values. So when n is 2, so this n by 2 minus 1 is actually 0. So only I equal to 0. I equal to 0 means we compute the first half as f of omega n to the power 0 is computed as fe of omega n by 2 to the power 0. So this is the first component of the DFT, first and only component for n equal to 2, plus omega 2 to the power 0, which is 1. So first multiplier is 1, FO, the only value we get FO. So we have to add. And for the second half, just flip the second value. Flip the second value means we have to subtract. So getting this idea, we perform our computation here. So 2 and 0, how they are combined? First half we add, second half we subtract. Very simple. So first half 2 plus multiplier is 1 because power is 0, 2 plus 0. 2 plus 0. For second half, just flip the sign, 2 minus 0. We get this as 2, 2. Here also identical computation. Add 1 and 0. For first component, second component, flip, subtract 1 minus 0. We get 1, 1. Now for final values, we have to compute the value of omega 4. So omega 4 we compute. Omega 4 is computed as e to the power 2 pi I by 4. E to the power pi by 2 I. We get value I. So omega 4 value is I. Now once again, how we combine the two. So once again we see the same formula. Just remember the same formula. For first half set of values, we have to add the corresponding values with powers of I. So I, its power will range from 0 to 1 for first half, then for second half just flip the sign. So the values now will be this 2 plus this 1. This is the first set of value. Why 1? Because y multiplier is 1, because I to the power 0 is 1. So we combine this as 2 plus 1. Now for second value, the second component 2, here also second component, how they are combined, now the multiplier is I to the power 1. So 2 plus 1 multiplied by I. So earlier it was 2 plus I to the power 0 multiplied by 1. Second will be 2 plus I to the power 1 multiplied by 1. So we get 2 plus I. Now the remaining values, simply flip this sign to get the second half. So 2 minus 1, 2 minus I. Evaluate this as 3, 2 plus I, 1, 2 minus I. So this is DFT of the original vector 2, 1, 0, 0. Now exactly very similar computation we perform for the second DFT. DFT of 3, 2, 0, 0. Now we know how to compute, again using FFT. We know how to compute the original problem 3, 2, 0, 0. Separate out even and odd parts. Even part is 3, 0, odd part is 2, 0. 3, 0. Even portion, odd portion is 2, 0. So once again we separate out odd and even parts as 3 and 0. Here 3, 0, and here as 2 and 0. These are the base problems, and for base problems the corresponding DFT is the same, will have the same value. Now how we combine? So we know how to combine 3 plus 0 first part, second part 3 minus 0. 3 plus 0, 3 minus 0, we get 3, 3. Here similar computation, 2 plus 0 and 2 minus 0. 2 plus 0, 2 minus 0, we get the vector 2, 2. So finally we combine so just remember in here computation, remember the values, omega 2 was -1 and omega 4 is I. So now we combine with omega 4, which is I. So again the values are this 3 plus I to the power 0 multiplied by 2, first component we write it as 3 plus 2, second component, second value 3, here also second value 2, 3 plus I to the power 1 multiplied by 2, we get 3 plus 2I. Second half, just flip the sign, 3 minus 2, 3 minus 2I. Compute this as 5, 3 plus 2I, 1, 3 minus 2I. So now we get our DFT values. So this is step 1 is completed, step 2 is completed, now step 3. So step 3, just simply multiply the two DFT values. DFT of f1x, just pointwise multiplication, DFT of f2x. Compute this as 3 multiplied by 5. I will just write the values, do not evaluate. 2 plus I, 2 plus I multiplied by 3 plus 2i, then 1 multiplied by 1, then 2 minus I multiplied by 3 minus 2i. Just simplify this to get the value 15, 4 plus 7i, 1, 4 minus 7i. So this is step 3. Now step 4, we have to compute its DFT inverse. DFT inverse of the same vector 15, 4 plus 7i, 1, 4 minus 7i, using the same FFT algorithm. So for inverse, computing DFT inverse using FFT, just remember 2 changes that we have to do. First is simply take reciprocal of all omegas. Second, only at the final step divide the result by n, where it is 4. So now we take our original vector 15, 4 plus 7i, 1, 4 minus 7i. This is our original vector. Initial steps are identical. Separate even coefficients and odd coefficients. Write this as 15, 1, here second write 4 plus 7i, 4 minus 7i. Again separate out odd and even coefficients, 15 and 1 and 1. Here also separate out, we get 4 plus 7i and 4 minus 7i. Now we combine them. So just remember the change. We have to use omega 2 inverse. Omega 2 inverse is, omega 2 is minus 1, inverse of minus 1 is minus 1 itself. So very similar computations. Combine 15 plus 0th power of omega 2 inverse multiplied by 1 and then flip the sign. So actually it is same, 15 plus 1 and 15 minus 1. So 15 plus 1, 15 minus 1, we get 16 and 14. Similar computation here. How we combine? First add, then subtract. So first we have to add 4 plus 7i plus 4 minus 7i. Second component, subtract 4 plus 7i minus 4 minus 7i. Compute this as 814i. 814i. Now we have to combine the two. Again, just remember the change. We have to use omega 4 to the power minus 1. Omega 4 is I to the power minus 1 is minus I. This is the change. So here again idea is same. We have to combine 16.4 with 8.14i. So it is 16 plus 0th power of minus I multiplied by 8, which is actually 16 plus 8. 16 plus 8. For second component, take the second values 14 and 14i, and here the multiplier is minus I to the power 1, which is minus I. So 14 plus minus I multiplied by 14i. These are second set of values. Now for remaining second half, just flip the sign. 16 minus 8 and 14 minus I multiplied by 14i. And one more thing, for the final step, not at the intermediate step. Just see, in intermediate step, when we combine, we do not divide by n. N is divided only at the final step. So remember also to divide by, here n is 4, 1/4. Write this as 1/4 of. Perform the computations, we get 24, 28, 80. 24, 28, 80. Dividing by 4, we get the values 6720. So this is 6 plus 7x plus 2x square. So we get our answer. So the same idea we can use to apply integers also. Same idea is used.